Point of reference is a coordinate system. I'm talking about X and Y. That's what I'm thinking about here, an X and Y coordinate system. Our problems aren't going to be three-dimensional or very, very little chance of being three-dimensional. So we focus on two-dimensional coordinate systems. There are rules here, and they're going to evolve. Generally, you try and you choose a coordinate system that is lined up with as many forces as possible. That's the general rule. To choose a coordinate system that is lined up with as many forces as possible. However, if your system is accelerating, try and line up one of the directions with the acceleration. That should be a higher priority. If your system is accelerating, try and line up one of your directions with the acceleration. That should be a higher priority because it makes solving the problem easier. So in this case, it's not accelerating, so I'm going to choose sideways to be the X direction and up and down to be the Y direction. A coordinate system has to be at a right angle. So the X and the Y have to be perpendicular to each other. When you're doing this, what you're actually doing is establishing direction in 2 dimensions for your problem. You're deciding what you will call positive and what you will call negative. You're establishing for the problem all of the things that you believe you will use for your vectors. All right, once you have an established coordinate system, your next step is to use trig. Now, what you really should write here for step 3 is you must convert all off-axis forces into components. You must convert all off-axis forces into components. We haven't used the word component yet. We're going to in the second example. But I'll say it again. You're trying to convert all off-axis forces into components. This example has no off-axis forces. Off-axis would mean that it's like out here someplace. It's not along an axis. All of these are along an axis, so there's nothing to convert. So step 3 can be skipped for this problem. Which brings us to step 4. Step 4 is applying the appropriate Newton's law. Applying the appropriate Newton's law. It's a first law problem or a second law problem. Now, there's really just 2 things you're looking for. Is the object accelerating or not? If you can answer that question, you know which law to apply. If the object's not accelerating, it's a first law problem. That's what this is. This is a first law problem. It is a statics problem. If it's accelerating, it's a second law problem. Now, this part is I know it seems ridiculously easy, but first law problems are not accelerating. But be careful, that doesn't mean they're not moving. They're not accelerating. So an object at a constant velocity is a first law problem. An object at rest is a first law problem. This is a first law problem. Now, in your notes, section 4, you need to have the definitions of the laws. That's what we're going to go over now. This first one is a first law problem. The second one's going to be a second law problem, so I can give you what the laws are. Now, there's the colloquial definition of the law, which I mean, when I say colloquial, there's like the popular way the law should be stated, the way you've heard, and then there's the technical definition I want you to have. So I would encourage you to not write down the colloquial unless it helps you understand the law. The first one, the colloquial, you've heard it before. An object in motion tends to stay in motion. Have you heard that phrasing before? That's the colloquial. People say it all the time. A rolling stone gathers no moss. That's a statement. This idea that, things that are already doing something will stay doing it. That's what is meant by this first law. And it's become part of our kind of popular culture to say that. But the actual first law has more specifics in it. And it's used to help solve problems. So let me give you the law as I would like you to have it, which is an object will maintain its state of motion. An object will maintain its state of motion. In parentheses, you might want to write state of rest or state of rest. Some people don't realize that rest is a state of motion. So an object will maintain its state of motion or state of rest unless acted on by an external, unbalanced force. An object will maintain its state of motion or state of rest unless acted on by an external, unbalanced force. So, state of motion. External. Unbalanced. Let's hit them all real fast. You know what I mean. State of motion. We're talking constant velocity or at rest. That's what this law is about. Maintain its state of motion. So maintain its velocity. Or maintain being still. That's what this law is about. If one of those two conditions are met, it's a first law problem. External. This is probably the one that makes the least amount of sense to everybody today. But an object can't apply a force to itself. It seems kind of ridiculous, but that's what the word external means. It has to be something from the outside that pushes on the object. You can't push yourself around. I know you think you can, but you can only push yourself around if you grab onto something around you. You're actually using that to push you around. So if you go to stand up, you need the ground. Otherwise, you don't stand up. If you want to walk, you have to push against the ground. Try walking on ice sometimes, or just watch videos of it. It's pretty funny. So understand that something from the outside is required to move you. So the force has to be external. There are things called internal forces. They can't cause you to move. Unbalanced. We're going to refer to the idea of net. Net means the sum, to add up. There has to be some unbalance from adding your forces together. But if your state of motion doesn't change, then there's no unbalanced forces. The first law is all about striking balance. Now, there is a mathematical equivalent to this. And a lot of people think of it as an equation, but it's not an equation. It looks like this. This is the mathematical equivalent of Newton's second law. And I would strongly dissuade you from calling it an equation. Equation is something you can plug in. This is not an equation. This is a set of instructions. This is the summation. F represents any force. The bar above the F represents direction and clearly equals 0. This says to add up all of the forces, taking into account their direction and setting them equal to 0. That's what Newton's first law is about. It says to add up all of the forces, taking into account the direction and setting them equal to 0. That's what Newton's first law is all about. Now, here's the appropriate thing to know. Our mathematics prevent us from doing anything more than one dimension. So in our problems, we are always going to be separating this out into net force in the x direction, net force in the y direction, and so on. If it's a first law problem, they're all zero. Now, like I said, this is a set of instructions. When you look at this picture, do you see any forces in the x direction? Is there anything pointed to the left or to the right? So in this example, I wouldn't worry about the x direction. I would only worry about the y direction. The final piece of applying Newton's law is to follow those instructions, which says to add up all the forces in the y direction and set them equal to 0. I have a normal force in the y direction. It's positive. I have weight in the y direction. It's negative. I will add them up and set them equal to 0. The result of applying this set of steps will be to create an equation that can solve your problem. Now, I want to be very clear about this. In your notes, you should put that down, that the goal of applying Newton's laws is to create a custom relationship that fits your problem. Here's the thing that's different about this from anything else you've ever learned. There isn't a single equation that works for every situation. This is not about equations. You are using a set of rules to generate a relationship on the fly for your specific example. It will be different for every example. So you can't assume that they'll always be the same. You can't assume you can reuse this stuff. There'll definitely be similarities. But this is a process that creates something at the end. And it's the something that's at the end that matters. All right, so here we go. We're going to try another example. This is another single body problem. Multi-force. But this is a dynamic example with trig. It's dynamic because I think you know what's going to happen to the wagon. If you pull on it, will it just sit there or will it move? Will its state of motion change? Yeah, so this system's going to accelerate. This is going to be a Newton's second law problem. Second law covers acceleration. First law covers non-acceleration. So this is going to be a second law problem. We're going to follow the same rules. We're going to start back at the top by drawing a free body diagram, which means reduce my object to a dot. The very first thing I'm going to do is go through that list of steps where I'm trying to identify which forces are acting on the object. You should be the first person whenever I ask to yell out, yeah, the force of gravity is acting on the object. It's always going to be there. So when I say, is there any fundamental forces acting on the object? You are almost always going to be right if you say, yes, gravity is acting on the object. So go ahead, draw in the force of gravity. I'm going to draw a single arrow acting downwards on the object. And I'm going to label it the weight. Now, is the object in contact with any surface? That's the next one. Yes, there's going to be a normal force. But when you go to draw the normal force, remember, the normal force is responsive. It responds to other things that are happening. Do you notice that you're pulling on the handle of the wagon? Is it possible you could pull hard enough on the handle of the wagon to lift it off the ground? Yeah, so understand that you could be reducing the object's contact with the ground. The normal force from the ground is going to prevent the wagon from going through the ground. But that doesn't mean that the normal force will be equal to the weight every time. It won't be. In this case, I think because we're already pulling up on the wagon, that the normal force is probably not going to be quite as big as the weight. That sum of the upward force in this problem is probably going to come from me pulling up on the wagon. Now, before we go any further, just stop and give me just your full attention for a minute, and don't worry about writing something down. Do you think the wagon is going to sink into the ground?
No.
Do you think the wagon is going to accelerate upwards? I mean, do you think it's going to go flying into the air? No. When you pull on wagons, they tend to roll across the ground. The reality of the problem is you're probably not pulling the wagon off the ground, but it's probably also not sinking into the ground. I think there is some balance in this problem. I think the problem is balanced up and down. I think the wagon's probably going to accelerate to the right. That makes sense to me. And it should make sense to you because you've probably pulled a freaking wagon before. So don't throw away your common sense. Use your common sense. There's going to be some parts of your problems that are balanced and some parts that aren't. We're trying to predict what we think the balance is going to be. You'll see why this prediction helps. But we're going to have to draw on a third force because there is the force from the handle. This is a tension force. It's a pulling force. I have a connection to the object, the handle, that allows me to apply a force in a specific angle. So that fits all the qualities of a tension force. So draw in your tension force. This is where you should be as careful as you can about the angle to try and mimic the angle given as closely as possible, and then label it appropriately. All right, so we are looking at a completed free body diagram. A complete free body diagram has just the forces acting on the object in it. Putting in a coordinate system isn't wrong, but it's not necessary. So if you are asked on the exam to draw a free body diagram, you are actually done. And this is the part that you will be graded upon. However, drawing in your reference system is necessary to solve the problem. So you may want to have a separate diagram that you use for working the problem that is different than the one you turn in as your free body diagram. But so far we have free body diagrammed, and now we're on to step 2. Step 2 is X and Y, coordinate system. Provide your reference. It seems to me like I know the direction the system is going to accelerate. That is the priority that I should use for drawing reference. And I think all of you would agree that if it's going to accelerate this way. And I'm going to make that way the positive X direction. Choosing a coordinate system lined up with the acceleration should be your priority. Everything else should be easy. Negative X has to be in the opposite direction. Positive Y has to be perpendicular to X. Negative Y has to be in the opposite direction as positive Y. Your coordinate system should work itself after you've chosen the direction for X. So I have chosen a coordinate system that I believe is aligned with the acceleration of the system. It's going to provide my reference. Make sure that the angle you are given is given relative to the coordinate system you drew in. Figuring out the angle isn't always easy. Okay, that's step 2. Going on to step 3, trig. We've already talked a little bit about this in a prior part, of class when we were talking about like velocities for objects that are, accelerating at an angle. Components are 2 vectors that make up a third vector. We've talked about this already. The tension is the only force that's not lined up with X or Y. In order to analyze this problem, I need component vectors that are lined up in X and Y. So doing the trig tends to be the part that's tricky for students. I'm going to tell you some hints, some things that will help. First, you're going to have to draw a right triangle. And there's some simple rules you can use to make this easy. Draw a right triangle that wraps around your angle that's lined up with your cardinal directions. It's a complicated sentence, Some of you know what I'm asking you to do, some of you don't, so I'm going to say it again. Wrap a triangle, a right triangle, around the angle that is lined up with your cardinal directions. So, I'm going to start drawing a triangle by drawing one side and start wrapping it around the triangle. I'm really going to be drawing the adjacent side first because I'm wrapping it around this angle. It has to be a right angle. And I need it to be lined up with the X and the Y direction. So it can't just be any right angle. It has to be lined up with the X and the Y direction. That's why we choose our coordinate and our reference first. This right triangle will contain two components. It will contain an X component and a Y component. I don't want to fuss with the trig too much right now, but you should be able to notice that this is a right triangle, and from this right triangle, you should be able to write Tx in terms of T and Ty in terms of T, which means sine and cosine. You'll notice that Ty is the opposite side and Tx is the adjacent side, and T is the hypotenuse. So I am not going to spend a lot of time with trig right now. All right, so for the time being, I'm just going to reference Tx and Ty. But Tx is T cosine theta, and Ty is T sine theta. And every single problem will be different. They're going to give you an angle for reference, and you have to use the angle they give you. So don't assume x is going to be cosine and y is going to be sine. For I guarantee in our very next example that won't be true. Now, I would strongly consider doing this next step. It's not for the judges, it's not for the graders, it's for you. I would really consider sketching this out again, but just with components, like this. There's a normal force up. There's weight down. There's a Tx in this direction, and there's a Ty in this direction. Now, I'm doing this because I want you to see something kind of specific. Notice how I stacked these two arrows together? The goal here is to help you recognize that those two vectors together probably counter the weight. They're probably balanced. That's why the wagon doesn't accelerate upwards or accelerate downwards. Also, it helps you take a look at the bigger picture and note that this system appears unbalanced because of one unbalanced force. I would strongly consider doing this. It will make the next step slightly easier because we're going to have to consider how to deal with these forces now. Which brings us to step 4. Newton's laws. Once you've done all this, now we can apply Newton's laws. This is Newton's second law. It's an acceleration. This object is going to accelerate. It's unbalanced. You are looking for either unbalance or acceleration. That's how you know it's a second law problem. So sometimes you won't know. They'll have to tell you. They'll give you some simple or maybe hidden information. But if the velocity changes, it's a second law problem. That doesn't mean it's speeding up or slowing down. If the object changes direction, it's a second law problem. So be very careful. Any change to the velocity, including direction, is a second law problem. Now, Newton's second law sounds a lot like Newton's first. I do want you to have the text of Newton's second law specifically in your notes. And here's the text of Newton's second law. If an object is experiencing an external unbalanced force, do I have to repeat that, or can you kind of get the gist of it? It's like the same phrasing as the last one. If an object experiences an external unbalanced force. Then the object will change its state of motion. Then the object will change its state of motion. It will accelerate. You should write that. It will accelerate. The amount of the acceleration depends on the inertia. The amount of the acceleration depends upon the inertia.